So let us summarize a waveguide, a rectangular waveguide, and then for your better understanding and give you some intuition. So basically, right, rectangular waveguide is form is this along. This is G and X and Y, right? And then this is A. Dimension along X is A and dimension along Y is B. We have this metal structure, basically, right? Like this metal structure to guide wave to this direction. So wave is beta is this direction, right? So for T case, TE means transverse electromagnetics. So EZ should be 0 and HZ should not be 0, right? So HZ, so we start from HZ, and HZ means this direction, right? So HZ has a value in all the surfaces, right? So that HG should follow cosine KXX, cosine KYY. That means, right, X is A, and 0 and A, and Y is 0 and B. All the four surface HG, because this is tangential to this order surface, all the value at the boundary should be some value, so that we should follow the cosine. We should have cosine trend for both. So from here, right, so we have EX and EY, HX and HY, right? So HEX is this, right? This one. So this surface, EX can have some value, right? That means axis should have cosine term, but this x term along this boundary should be 0, because E field should be perpendicular to this metallic surface. So this is sine k y. EY should be opposite, right? The HX is follow a different opposite trend with EX, so it should follow KX x cosine KY y, and HY is opposite trend with this, so it's KXX sine KY y. So from here, so TE 00 is not possible, right? If T0 is not T, so KX is KY is pi. This is M B, right? So T is 00 means Mn is 00, right? So this is not possible, because this EX and EY both become 0. So TE10 and TE01, but TE20 is possible, right? So, and so on. TE and M, except GG is possible. 00 is possible. It's all possible, right? And then about TM, so basically this is start from HZ should be 0 and then EZ is not 0. So we start from EZ, but EZ, right, EZ, if this is E field is along the Z direction, this is or tangential to all the four surfaces, right? So that tangential electric field should be 0, so that EZ should follow sine kx sine ky. And then the other is EX, EY, HX, and HY. This trend should follow from this. It should be same. So for TM case, because EZ has a sine and sine, right? Actually, I omit this one, right? So every term should have this, because all the wave is this waveguide for maintain the wave propagating to the plus G direction, right? So everything should have this. So TM 00, TM 10, or TM 01 is not possible, right? TM 11 is possible. So for TE, so we can calculate characteristic impedance, right? Characteristic impedance. T case T, characteristic impedance of TE is EX and HY. Basically, our assumption is wave is propagating positive Z direction. So if E is X, H is Y, then we maintain this sign. But we have another one, right? EY also, and HX here. So we can put EY and HX, but we should put minus, because to follow right hand rule. So if we plug this one, if you see the book, then if you see all the detailed equation, then you will have this ratio. So basically, so this is same as K beta times eta, right? So K is, if this waveguide is filled with some material, right? Here, so it can be vacuum or any material. It has epsilon and mu inside, and K is determined by this. Eta is determined by this, right? So that means this is kind of same as parallel plate waveguide, right? So this is larger than eta. For TM case, eta TM, so this is also same. So if you use equation from the book, so this is beta omega E, so which is also same as this. So here also K and eta is shown here, same as this, and then this is smaller than eta, right? So this is also following the equation for the parallel plate waveguide. So all the ratios are maintained, and then this ratio is represented as eta, TE, and TM. So let us have some kind of concept about how the fields are excited in the rectangular waveguide. So I said dominant mode is TM10 mode, right? Which has the lowest cutoff frequency. So for this case, KY is 0, right? Because N is 0. So if we plug one over here, this all term will be gone, right? This related term. So that HZ follow cosine KXX EX becomes 0, HY also 0, EY is not 0, EY follow sine KX X, HX follow sine KX X, right? So for this case, we have a Y term. So if we draw TE case, right? So X, Y. So let's say we have this kind of box. So waveguide is here. So wave is propagating to this direction, right? And then, so electric field is Y direction, right? So Y direction we can draw like this. So because at the center, right, electric field will be high, but as it goes to the boundary, electric field along the Y direction will be smaller. And then half of this is half of lambda z, right? So lambda z is right. So after half of lambda z, electric field along Y direction will be opposite. This is general trend you can think of, and then H field along this. So because wave is propagating to the Z direction, if we use right hand rule, E field is this and H field should be this direction, so that beta goes this direction, right? So H field should follow this direction. You can also at the bottom you can have this one, right? So after maybe lambda, maybe so another one is here, right? But this should be opposite direction. So basically TE mode is shown like this, right? So you can have, imagine you can have some image of this TE mode, TE10 mode excitation, right? So let's see TM mode. So TM TM mode with minimum number of NM is TM11 mode. So for this case, if you see TM mode from parallel plate waveguide, you will understand maybe better. So let's say we have this structure. So for this, TM is completely different, right? So for electric field, so let's say this is half. Electric field is right. Electric field at the edge, at the surface, should be perpendicular. So basically, it looks like this. So because for this case, Hz is 0 and Ez is not 0, right? So for this case, we have Eg field. You see, right? So E field should have some perpendicular component at the edge. It is shown like this, and then below it should be similar. So on the bottom also, something like this, and then bottom also would follow same pattern, right? Like this. So just make sure so right here, something like this. So if we see electric field, so it looks like this electric field. Right? If you see this one is completely different, right? This and this completely different. And then H field is it's following this. So H field is following this. H field should have tangential to all the surface, right? So that pattern will be like this. Right? And then to maintain propagation to the z direction, electric field H field should follow this direction. So E is here, H is this, beta is this, right? So this will be opposite direction. Yeah, so this is TM mode, right? So if you see these two things, we see completely different story, right? So easy, it's not 0. For this case, HG, G is not 0, right? HG. So just to have an idea, right? How does it look like TE mode and TE10 mode and TM11 mode in the waveguide, so that you can distinguish what it is, right? Okay, and then finally, what I want to cover is again one thing that I want to cover finally is this one for your understanding. So we have this relationship for the rectangular waveguide, right? So I let you know this kind of this relationship, right? So omega and beta diagram, or I call it dispersion, right? Dispersion diagram. So this is also important to understand this kind of waveguide property. So for TEM wave, right? TEM wave basically this relationship TEM case. Omega divided by beta is, this is velocity, right? So this is this TEM wave follow simple relationship. So it's kind of W and B slope is constant, right? So it doesn't change as frequency changes, right? Beta and omega is always constant, this TEM case. But if we plug this one, this will form like this. So as Mn number increases, this will be moved like this. So I'll give you assignments, homework to let you draw with specific number A and B and M and N. So you can practice and draw by yourself. So this TE10 mode, or let's say this is TE10 mode, TE01 mode. So let's say A is bigger than A in this case, right? So we'll follow this kind of drawing. It's not like a straight line. So what that means, so if we just pick some point here, right? So if we want to know that phase velocity, right? Vp. Vp is omega divided by beta, right? So that means the value here, right? The slope over here. So this is a beta and this is omega, right? So this slope determine omega p. If we see Vp, right? If you see the slope, this is larger than this, right? Larger than this velocity. So this is one thing you need to know, one thing you can understand from this dispersion diagram. And then this is phase velocity, right? Phase velocity. And the group velocity, right? Group velocity is the slope, right? Differential derivative of omega in terms of beta, right? So the meaning is slope. Slope, right? This slope determine group velocity. So this is two different things you can understand from this diagram. So one thing I want you to think of is what is the meaning of this point? The meaning of this. What is the meaning? So just think about it. I will assign a homework, so you will easily understand what does it mean. So I want you to think of it by yourself. And another thing is actually, right? So as I said, the phase velocity inside a waveguide, rectangular waveguide, is WP. Let's say this is VC. So VP is larger than VC, right? So how can you understand this? So let's say we have a waveguide, right? And then some wave is propagating this direction. This is wavefront, we say. So this is a solid line is maximum, and then dotted line is minimum. So wave is let's say wave is propagating this direction. So it's a max minimum max minimum. So what does it mean? So if we draw extend, wave is following like this. This is max. So this is max, mean. Right, so wave is propagating this direction. This is waveguide, right? This is so let's say this is lambda 0, right? Some electromagnetic wave. TEM wave is propagating this direction, but with this kind of waveguide structure, wave is bouncing back and forth. So some maximum minima is happening like this. And if I draw another one, this is max, mean, max, mean, max, mean. So if a wave is propagating this direction, right, incident with this direction, and another one this direction, right, this one and this one. So this orange one also, this blue one also has a maximum, minimum, maximum, minimum, right? So if you see this one, this is a maximum, right? Because max and max is cross, and then this mean. So what does it mean? This is max, mean, and max. So if you compare with this length, lambda 0 divided by 2, this one, right? This length is longer than this lambda 0 over 2. So max to max will be lambda z, right? So the guided kind of wavelengths. So lambda z is definitely longer than lambda naught, right? So that phase velocity can be given as this. If we change this lambda z to lambda, because lambda z become larger, then this is omega and beta, right? So beta becomes smaller, k, similar as this, so this become larger than omega c, right? That means omega divided by k, right? K is, right? So that is the meaning. So that what that means, the phase velocity is faster than velocity of light. So this is normally happening in waveguide structure because this lambda z is longer than lambda naught, because this superposition of two wave inside a waveguide. So this can be understand. It's also corresponding to this one. This slope is larger than this slope, right? So this is corresponding, and then this is the way how you understand, right? All right, so let's wrap up